Thanks for that, Ray. Welcome, everybody. So I'm Giles. This is Rasto. I'm going to sort of do a few slides giving an overview of VPP. So I guess it's been alluded to today. I know earlier I talked about BPF and XDP, talk about vectors. Well, I'll give you a sort of overview of that. Then Rasto's going to go into Contiv VPP, which is a CNI plugin that we built using VPP, where I guess we're about to disagree with Chiara on the thing about using the kernel to connect containers. Sorry guys, no, we keep it in user space. But hey, a bit of controversy is always good. So what is VPP? So we said the universal data plane, and really, the history of this, the sort of genesis of this was it came out of Cisco. It was initially like a sort of punt path software forwarder, but then we realized it was pretty good and we should probably open source it. So it's been open sourced through the Linux Foundation. So it's part of the LFN, Linux Foundation Networking sort of umbrella. The key thing, and again, sort of, if you remember earlier, with BPF and XDP, this thing of, if you want to extend it, you have to build helpers, and the helpers have to make it into the kernel. So, there's an IP lookup, there isn't a bridge lookup yet. And probably the key reason that we've done everything in user space is the fact that that gives us that feature velocity. So if we want to put a new forwarding plane in, we don't have to wait for Linux to bless it. We can just push it straight in because it's user space. The throughput, that's the magic of vectors, which we'll come on to as well. Initially, in fact, it ran on PowerPC, but it now runs on ARM and, of course, x86, which is where you'll see most of it. The scope. So, in fact, the three bullets are nicely the opposite way up from the three on the picture. So the scope is the network I/O. Typically we're using DPDK there, though, we're open to other things. There's been other suggestions today, again, with things like XDP. There are some native drivers, I think, in VPP as well. VPP itself really knows about the packet processing, so about your actual forwarding. But then, of course, the key is we've got to set it up, so you need some kind of a management layer, as the control plane. But we don't live in isolation, so this is kind of just to give you a picture of the Linux Foundation networking and associated stuff and where the whole FIDO VPP thing sits. So VPP itself, when it got open source, we called it FIDO, FDIO, fast data. You can't pronounce FDIO, so it's a dog. So we sit here in the data plane. Of course, we sit on top of an operating system and hardware. Some of these other projects have been talked about already. So, for example, I used to work on Open Daylight quite a bit. That's been presented. ONOS has as well, which is another SDN controller. I think Emma's talking about OPNFV stuff after this. ONAP, strangely, no one's here talking about ONAP. So, has anyone here heard of ONAP? Well, maybe that's why no one's talking about it. There's only like 4 people with hands up. So ONAP basically is kind of a telco-ish thing. It sits on top of Open Daylight in terms of how it programs the network, but it's very much about how you provision telco-type services. So it's all unbelievably dull. I'm glad not to be working on it anymore. But I guess, in terms of buzz, and the room's quite quiet because we should have stuck the word Kubernetes all over everything to get everybody in. Really, Kubernetes is where it's at. And if you think about the stack now in container sense, what you're really saying is that your CNI plugin really does this bit, the network controller. And Kubernetes is really all about the orchestration and how do you deploy pods onto different nodes and how do you figure out where to put things and sort of, manage the life cycle. So the projects we have in FIDO, VPP itself, of course, the core. There's a bunch of different other projects around packet processing. So things like, Open Data Plane, P4 has been mentioned a few times already, I think. There's even, sort of information-centric networking and that kind of stuff. I mentioned, as I said, we typically run on top of DPDK in terms of the network I/O. And then at the top there, the management agent. So, Honeycomb really is about virtual machines. It's really a cut-down version of Open Daylight so that you can manage effectively an instance of VPP running on a node. But I guess the way I think about it is in that kind of VM world, you're still probably thinking about things like netconf and yang and BGP. You're very much in that kind of, I am a host, I am a router, whatever. So using those kind of more, I hate to use the word legacy, those more like legacy approach to configuring things. Because really, if you think about it, as you move to containers, like how often do you want to reconfigure a running container? So multi-tenancy in networking, traditionally, we built IPVPNs, right? And the way we did multi-tenancy was we used VRFs, and we could have like 100 VRFs on a router. Multi-tenancy with containers more likely means spin up 100 containers, one per tenant. And reconfiguration probably means take this container, blow it away, and create a new one. So our way of doing things is very different. So what we've done to be more sort of cloud native in the container world is we built the Go binding onto VPP. And then what, in fact, probably is, oh, I've got a few more slides, haven't I? Then Rasto's really going to go into Contiv VPP, which is a CNI for container networking. So it pretty much sits on top of Go VPP and provides container networking. We have a whole bunch of test stuff. I know that Ray and the absent sick Maciek were going to present C6, so I guess Ray's going to do that on his own. Some other interesting test stuff in there. For example, T-Rex is like a high-performance packet generator. So what does all this stuff mean with vectors? You know, how does it actually work? So I'll skip through this because it's restating what I've already said. Oh, going the wrong way. Here we go. So basically, you decompose packet processing into a graph of nodes. And by nodes here, we just mean little chunks of code that we kind of chain together. So, you know, classic, you know, you're forwarding a packet, what are you going to do? You're going to get the packet in, you figure out from the driver that this is an Ethernet packet. You then say, oh, actually we found out that it's IPv4, so we're going to IPv4 graph node. We then do a lookup on it, and then it might well be that we're forwarding it, so we have to rewrite it, put it out of a different interface, that sort of thing. So we break it down to little nodes, which are kind of micro network functions. And then the packets move through this in vectors. So again, multiple people have talked about this already, the concept, not so much the vectors, but the concept that, you know, don't have one interrupt per packet, or don't poll and just pull one packet. You know, try and pull as many packets as you can at a time. So typically, DPDK, we're in polling mode. If the load's high, we might get back 20, 30, who knows, a whole bunch of packets that were waiting for us. So we process them as a vector. And this is where the graph comes in, because the graph nodes fit in the instruction cache. So the goal is that your graph node fits in L1 cache. And if you know anything about CPU cache hierarchies, that's going to give you orders of magnitude more performance than going off to main memory. The packets themselves are prefetched into the data cache. The other thing to say is, of course, when you do things like lookups, one of the challenges becomes, well, what if you have a million routes in your routing table as you would in the internet? And the answer is, of course, that we can, again, sort of parallelize all those lookups. But it takes a while for memory to get back to us with the first lookup, but we can then be doing the next one and the next one and the next one, rather than stalling, waiting for that first lookup. And yeah, I think that what's interesting about this is, I mean, last time I programmed in assembler, it was like 6502 or something, and you know, there was no cache, there was none of this sort of intelligence. But the people who built this...
Back when dinosaurs walked.
Yeah, exactly. I've been accused of being one. And the people who came up with this stuff, you know, really understand CPUs and modern CPUs and cache hierarchies and how all this stuff works, and that's the genius of it. And the sort of proof is in the pudding. I mean, again, Ray will probably talk about it, but when we went from sort of generation N to generation N+1 of Intel CPU, the performance handily went up because it was taking advantage of it automatically. So in terms of the actual packet processing, good, we're going okay for time. So we have the graph we mentioned, so the individual sort of steps in it, the graph nodes. I coloured the input ones differently because this is really where it's coming in from your network driver. Or, of course, you know, realistically, of course, one thing to say is that I would say this, of course, working for Cisco, but it's probably fairly unlikely that people will be deploying this in boxes with multiple network interfaces acting as routers. You know, please don't do that. We want you to buy our routers. But so more likely, we're talking about something running on the host as a vSwitch, and so quite a lot of your packets are going to be coming in through something like vhost user, rather than coming off an it. So you have a vector of packets. They come from one of the input nodes, and then, as you see, they're going through step by step, rather slowly because of my useless animation. And the point is, at each point, that first packet in the vector is going to be warming up your L1 cache, and all the other packets in the vector take advantage of that. But of course, we also, in some cases, are going to have to split the vector. So imagine there's an ARP mixed in with a bunch of V6 packets. You'll have to split it, and in that case, of course, the ARP itself will have to warm its own cache up. Plugins. So, you know, as I mentioned, the whole point here is that you should be able to add code quickly. We can add it quickly, but so can you too. And so how does that work? Well, plugins really, you just plug new nodes into the graph, they can be run sort of separately from the main VPP code base, so they can be effectively first-class citizens, but you don't have to be merged in and go through all the CSIT stuff that people like Ray and Maciek do. So yeah, you're building it yourself, but to all intents and purposes, it has equal status with the rest of VPP. But of course, also you can have hardware plugins. So imagine you have a NIC, and much to Luke's annoyance, this is an intelligent NIC, and this NIC does whatever it might be, IPSEC offload. We'd like to be able to take advantage of that. If the hardware supports it, let's do it in hardware, not in software. Right.
Oh yeah, you've got like.
Yeah. So yeah, as Giles said, the main topic of this presentation is actually the project Ligato, which is I would say a platform for building cloud-native network functions based on VPP. So before we go there, we may need to clarify what actually a cloud-native network function is. According to CNCFIO, cloud-native means building the application as a set of microservices, which are packaged into containers and orchestrated by some orchestration software, typically Kubernetes or something else. So with CNFs, basically we aim to do the same. Instead of deploying monolithic network functions, we split the network functions into multiple loosely capped pieces, deployed as containers, and interconnected, if possible, with the fastest links between them. In case of VPP, we put VPP into containers. We can use an interface called MEMIF to interconnect the VPPs running in different containers on the same node, and in which case the packets would go to shared memory between the containers. In case that some of the pods are deployed on a different node, then it is a different story, but in that case we can leverage DPDK, etc. And yeah, to put VPP into containers, we basically need some management plane or control plane of this stuff, and that is basically Ligato. That is the control plane part of building cloud-native network functions based on VPP. Yeah, this is how it would look like in case we deploy this into production. Let's say we have two hosts, and we want to deploy some cloud-native network function that is represented as some chain of network functions through which the traffic needs to pass in order to do the overall network function that we need to achieve. So in case of this, you have different VPPs running on each node. We usually use one of them as the vSwitch VPP, and then we deploy multiple CNFs on each node. And we need to somehow consume the logical representation of the service function and render that into physical topology, which means that we need to have a management agent running in each of the containers deployed on the nodes, and we need to have some entity which basically processes the logical representation into configuration that will be programmed to each of the VPPs. And yeah, as I said, Ligato is a development platform that allows you to do this. It allows you to do the service function chaining, as shown here. Part of it is a service function controller, but even most important part is the VPP agent that we deploy together with VPP inside of each container. So as we decided that we want to build network functions like this, we pretty much decided that we need to build a new management agent for VPP because those that were available were not really good fit for the cloud native case. Yep.
Sorry. So in this case, then Ligato is your control plane agent that talks to your CNI provider.
Yeah, in this case, Ligato actually has several components. One of the components is the VPP agent that sits in each of the containers next to the VPP and is able to program the VPP. And then there is one more component as part of the Ligato project, and that is a SFC controller. And that is the component that is able to process the logical representation of the chain into the partial configurations that will need to go into each VPP agent and programmed to VPP.
Yeah, it's probably the same with Contiv VPP. So when we hook in with Kubernetes, we use the VPP agent, but then we don't use the SFC controller for that.
Yeah.
Unless you're also running CNFs as well as Kubernetes, because that's where the CNI sort of hooks in with the VPP agent. Okay.
Yeah, we'll get there. Yeah, as I said, the VPP agent is a new management agent for VPP, which was designed, for this cloud native use case. We decided to use protobuf APIs as opposed to netconf or restconf, which you can get from Honeycomb. Pretty much the same API that is defined by proto messages can be used to program the VPP through any transport that we support. So you can either choose RPC-based way of putting the configuration to the agent, in which case you would use the REST or gRPC, or you can use the data store way of putting the configuration to VPP. For this we support ATCD, Redis, BoltDB. And we also do support message brokers for streaming notifications. As we were designing this, we decided to use the Go language to build the new agent, because we knew from the very beginning that we will need to integrate with Kubernetes and Docker and that kind of stuff. So that was pretty much a clear choice. And since we need to have the agent packaged into Docker container together with VPP, or to a pod together with VPP, it also has to be compact and small footprint, which would not be the case for the Java-based agents. But for the Go-based agent, it is actually, just a static binary that you put into container together with VPP. Yeah, as you probably know, if you want to program VPP, you need to use binary APIs. Those APIs are quite low level. They use like numeric references to interfaces, and you get byte ordering issues there, and you use bitflex to configure stuff. As part of the building the agent, we created the Go VPP project, which is part of the FDIO. And that is basically Golang wrappers over binary APIs. So you have binary APIs, and we produce a generator that is able to generate the Go structs that basically reflect the binary APIs. And part of the Go VPP, we have a small infra that is able to marshal and unmarshal the Go structs into binary and send to VPP and communicate with VPP. The VPP agent is part of the Ligato platform or project, so it is not part of the FDIO. It uses Go VPP to talk to VPP, and as I said, it provides more high-level APIs. So, in case you would need to configure VPP over binary APIs, you need to care about the versioning, because each version of VPP may have different version of a binary API, and that needs to exactly match. Then you need to care about message ordering. For instance, if you want to configure an interface and have a static route that is pointed towards the interface, you first need to create the interface, apply IP address, and then create the static route. So this is what VPP agent does for you. You just put everything what you need to have configured on VPP to the VPP agent, and it would automatically handle all dependencies between the configuration items. It would handle some error states, so it is able to do the retries on error or some auto healing. It is able to handle restarts, etc. It is also very modular, so if VPP is a set of plugins for the forwarding, then VPP agent is a set of plugins for management. So if you, for instance, develop a new VPP feature, you would build it into a VPP plugin. You can similarly write a new plugin for the VPP agent and just put it into the infra. And VPP agent we package together into a Docker container with VPP. So if you take any version of the VPP agent Docker container, you always have the management agent with VPP inside the same container image, so you have no versioning issues. This picture shows some architecture of the VPP agent. As I said, the center part is the plugins that are used to configure VPP through binary API. Apart from VPP, we do have also Linux plugin, which can configure, the Linux interfaces and stuff like that which is needed in case you need to use this for containers. And the bottom part is the APIs that we expose. As I said, you would use the same protobuf API data model for any transport that we support. Yeah, and so this was basically the infrastructure part, the Ligato project. So as I said, the Ligato provides the VPP agent plus the service function chain controller, which can be used to build the forwarding chains. The Contiv VPP is actually an application of the VPP agent. So we took the VPP agent and integrated it into Kubernetes ecosystem. Basically, we just extended the APIs of the VPP agent in the Ligato project, and we just added Kubernetes API on top of it. And as the result of that, Contiv VPP is basically a CNI plugin, generic CNI plugin, which can be used in any Kubernetes cluster. And if you deploy it, you get VPP running on each node, providing the connectivity to the containers. And at the same time, it still exposes the same APIs as the Ligato VPP agent. So if you want to, extend the default behavior of the CNI plugin, you just use those APIs to, for instance, create a new interface into the pod, which would be used for some different purpose. This shows some architecture of Contiv VPP. So with Contiv VPP, after you deploy it, you get a Contiv vSwitch running on each node in the Kubernetes cluster. Inside of the vSwitch pod, you have VPP and the VPP agent. And of course, you can use the APIs to somehow program the VPP, but you automatically get the programming of the Kubernetes pods connectivity from kubelet through Contiv CNI. And apart from the CNI plugin, we have another connection to the Kubernetes state of the cluster through our components Contiv CRD and KSR, which are basically just the reflectors of the Kubernetes view on the cluster into our instance of ATCD, which is basically consumed by each agent in the cluster. This is how networking looks like if you used Contiv VPP. This is on two-node cluster or multi-node cluster. This is what you get by default. So, as I said, one VPP on each node, connected to data interface through DPDK interface. And then we have one verb for pods. That's basically just a preparation. Later we want to provide multi-tenancy, so you could have multiple verbs per tenant, and each verb could be, each set of the pods could be separated from the other tenants. And then you have a bridge domain that is used to interconnect, to form the overlay network and interconnect between the nodes. And each pod is by default connected to VPP through a tab interface, only because we need to support any generic application. So either you have, a web server or database running in the pod, it needs to work. But of course, there are options for faster connections than the tab interfaces, and that would be on the next slide. So what I've shown on the previous slide is basically this cloud verb part of the picture. So if you deploy Contiv, automatically with each pod, you would get an interface connected to the cloud verb on Contiv VPP running on the host. And as I said, you can still use all the APIs that we provide in the Ligato VPP agent to, for instance, create faster data plane interconnects between the vSwitch VPP and the VPP that might be running in the container. And you can use SFC controller, which is part of the Ligato part, to orchestrate basically this left part of the vSwitch picture. Okay.
This is not part of an extension, the API extension of Kubernetes, the SFC controller.
Well, SFC controller is part of the Ligato project. It's open source, and the Contiv VPP is just this part of the picture. But you can deploy it together on the same cluster.
You could define the SFC API as a custom resource definition for Kubernetes.
Currently, the SFC has only its own API, but there are other options. You can actually use something else instead of SFC controller. For instance, there is a network service mesh concept, and that would be another way of doing these chains. Okay, I think we are running over time, so I'll just briefly go through some load balancing stuff that we do with Contiv VPP. With Contiv VPP CNI, we have our own implementation of kubeproxy, which is running completely in the user space within VPP. This shows how the programming of the kube proxy looks like, quite complex and complicated. But the key message is that we do all the load balancing and netting on VPP, so you don't need to run kubeproxy unless you want to have a pod that is connected to the host networking, in which case you could still use kubeproxy to do the load balancing and netting. This example shows some deployment with Contiv VPP. There is actually a mistake. I have 2 replicas of Nginx defined here, but there are 3 replicas running in the actual cluster. So I defined a replica set with 3 web servers. I covered that by a service of type load balancer, which exposes basically 2 virtual IP addresses that are NATed to one of those backends. In case of cluster IP, that is an IP address that works within the cluster. In case of external IP, you need to have an external load balancer. In this case, we have Metal B load balancer that is configured here, running in L2 mode. This would be the configuration of VPP that is rendered from that type of deployment. So we have a 1 gigabit Ethernet interface that is the PDK interface used for connecting the node. This one tab interface is actually the interface that goes to the top, to the pod, and those VXLAN tunnels are tunnels that go to the other nodes in the cluster. This is the NAT rule for the service that I have just deployed on the previous slide. So you can see that both virtual IP addresses are NATed to local IP addresses of the pods. And for the external IP, one of the VPPs in the cluster acts as or responds to ARPs using the proxy ARP. So in case we had this kind of deployment, 2 nodes, external load balancer, some router, then this VPP, for instance, would respond to that ARP request for that virtual IP, and all the traffic would be basically routed towards this node. And together with traffic policy cluster, it can be still load balanced on VPP to the other node. There is another mode of running these kind of topologies, and that is BGP based. In which case, both VPPs would advertise those virtual IP to the router, and then you could have proper load balancing. So this is one of the applications of the Ligato VPP agent, actually. And now, Giles.
Yeah, I'll try and wrap it up quickly, but yeah, this is another application, newer. I mean, I guess, we're thinking about history.
Yeah,
I mean,
about
Ligato,
1 year.
The first thing we did with Ligato actually was a cloud-based CMTS, which I think was announced last year. But that was sort of internal proprietary. If you want to do cable broadband, here's a cloud-based way of doing it. The next thing was Contiv VPP, which we open sourced. And then we're now looking at other applications. And here's an example, which is IPSEC. So VPP has IPSEC today. It has a full implementation with the forwarding planes, IPSEC, we have ESP, tunnel and transport, V4 and V6, all the various authentication and encryption algorithms that I don't really understand. On the control plane side, it has an IPv2 initiation and responder capability, and that has been interop tested with various other stacks. But I guess what we're seeing, though, is that people are saying, well, VPP is more about data plane, and these existing control planes like Strong Swan are very popular, very well known, and well understood, and they have great sort of HA modes and that kind of stuff. So why don't we leverage those? So today, typically, we see deployments where people are rolling out Strong Swan in virtual machines, and it'll just be a Strong Swan daemon using the Linux kernel for its forwarding, programming it through NetFilter. So the first step is to plug VPP in to the VM, and again, there's a couple ways we can handle that. We've done things like intercepting NetFilter calls, but ultimately Strong Swan has it's called Vici. It has its own kind of API for hooking things in, so we're integrating with that. But really, where we want to get to is these containerized deployments. So having a separate sort of containerized instance of that, and then still having a vSwitch in front of it. And as Rasto was talking about with Memif, so a single copy memory interface between a vSwitch instance, which might be doing VXLAN tunneling or whatever, to talk to the outside world, but then the VPP instance in the container that's doing IPsec.
So you told a very strong story about integrating Kubernetes with Ligato, and then the local, Contiv, and then Ligato, the local agent. So where does Strong Swan play in this? Are you building something like an IPsec appliance or something like that?
Yeah, this would be that kind of stuff. So you'd still have, and I guess that's what we come on to, eventually, you want to integrate with Kubernetes. So using something like Contiv VPP. The benefit of Contiv VPP, I guess, is that we just run one vSwitch for both the sort of IPsec data plane, but also for the Kubernetes kind of control and management plane. But I guess the other thing to think about with the stuff we're doing with Memifs, I know there's a talk coming up on, it's the next one, isn't it, about Maltus and stuff like that. And I guess that's what's interesting, is these different approaches. Our approach is to say, well, let's just have one interface that Kubernetes knows about, use that for control and management plane, and then we spin up these additional interfaces through the Ligato SFC controller, or in this case, we'll have almost like a Strong Swan controller that's based on the SFC controller. And those are kind of off on the side from Kubernetes' point of view, and we use those for the network data planes. But that's the kind of end goal, is to have it, so Kubernetes can, Kubernetes can take care of the placement piece of saying, okay, how many, run these as a replica set, like how many instances of these do we want to run, where do we run them, if one of them dies, spin up a new one. But then have the separate Strong Swan controller based on the SFC controller, which is programming these individual VPP instances in the containers rather than the shared one in vSwitch. So you might imagine, you're accessing corporate VPN at massive scale. The clients are all out on this end, coming in through a VXLAN tunnel, kind of like what Rasto was showing before with VRFs or bridge domains on a per sort of multiple VRFs. So one really for sort of southbound encrypted traffic, and then another one northbound for the unencrypted traffic, which is then heading off to whatever your secure applications are behind this. And I guess the goal is to be able to horizontally scale these instances of Strong Swan. The challenge, of course, with the horizontal scaling becomes that if you get any kind of rehashing happen, so like one of the containers dies and everything gets rehashed, then you'll get a packet for which you don't have session state. So you have to then have other ways of handling that. So for example, another KV store on the back end where if this container dies and this one gets their packet, it can look up, what's the state for that session? But as I say, Strong Swan itself has some pretty good HA, so there is stuff we can do where a certain number of failures can be handled simply through Strong Swan's own HA. And that's a good reason for using it. I think that was it, yes. So any questions? Other than from Ray? Yeah, go on.
I also, there's the Contiv VPP CNI plugin for Kubernetes, but I also saw a project from Intel which is called User Space CNI plugin. I don't know whether you've heard of it.
They are not related.
Okay, so what are your thoughts about that? I didn't try both of them in practice, but I saw that Intel's CNI plugin for VPP is like small binary, it doesn't have any additional demos, but at the same time it doesn't include any network policies, for example. So it's like straight from like having small architecture, but I'm curious whether you can thoughts about.
So I'm going to talk about user space next, and I agree, but yeah, I can get into that next.
Okay, yeah, I'm very curious about.
Yeah, I think Intel's one was really like kind of a proof of concept of CNI, whereas with Contiv we implemented full, support for Kubernetes services and policies. I haven't talked about that, but policies are also implemented on VPP completely. So we program ACLs on VPP on the interfaces facing towards spots. So I think that Contiv VPP is like more fully featured than that one.
Okay.
Okay.
Thanks, guys.
Thanks.
Guys, thank you very much.
I guess if there's more questions, come and grab us after.
So